Gravity is one of the fundamental interactions discovered by physicists for several hundred years since Isaac Newton. Everyone continuously experiences gravity throughout his or her lifetime. But have you ever thought that the gravity can also play a significant role in regulating the air temperature near the surface of Earth? This is the topic of today. Welcome to Intuition. This is a unique channel to explore, study, and share the knowledge about basic issues in physics and beyond. Let's go to Blackboard. Everyone knows that the surface temperature of Earth changes day and night. This is what we call the diurnal variation in the surface and air temperature. Everyone can do this measurement in his or her backyard by measuring the surface temperature and the air temperature as a function of time. In this experimental result, the lower solid line represents the surface temperature. So this is a sunrise, and this is the morning, and this is noon, probably around 1 or 2 p.m. And this is afternoon, and this is a sunset. So the surface temperature decreases dramatically after sunset. By way of contrast, the variation of the air temperature near the surface is a little bit mild. See? So this diamond dot represent the air temperature. During the night, the air temperature is higher than the surface temperature, but during the day, the air temperature is significantly lower than the surface temperature. As a result, the variation of the air near the surface is not that dramatic compared with the surface temperature. By the way, the upper one, the square dot, represents the soil temperature. In this case, is 5 centimeters under the surface. So that will give you another indication of this diurnal variation. So that makes the Earth different from other heavenly bodies, such as the moon and other planet without atmosphere. So that is very important features of the Earth where we live. But how do we explain this phenomenon? Now, here is my explanation. Before we go, we have to introduce some basic idea in the gas model. The atmosphere is made by air molecules. If you enlarge any spot at any position, then you should be able to find many small particles called air molecules. These molecules are constantly in motion in all directions. So therefore, the motion is primarily at random. It is important to understand that it is this mechanical motion of particles which determine the temperature of the air. So this is a simple formula to give you the relation between the air temperature and the mean value of kinetic energy of each molecule. Before we go further, we probably have to introduce what we call the internal energy of atmosphere, which represents the total energy of molecules. These UA represent the internal energy of atmosphere, which is the sum of the total kinetic energy and the potential energy. In our case, I only focus on the what we call the transnational kinetic energy, meaning the molecule is moved from one place to another in space. And from this expression, you can see that the total kinetic energy would be the sum of the individual molecules' kinetic energy. The potential energy can be counted one by one, depending on how many air particles in the atmosphere. Alternatively, you can introduce the total or the equivalent mass of the atmosphere and the mean value of the height to represent that potential energy of gravitation. So in this study, in this talk, I will simply use these two types of the energy in the atmosphere to explain the diurnal variation in the air temperature near the surface of the Earth. In these two diagrams, I illustrate that the vertical distribution of the atmosphere. By the way, the vertical axis represents the air temperatures above the surface, while the horizontal axis represents the horizontal direction represents the surface. So in these two diagrams, it is apparent that the vertical distribution of air are different. At night, most molecules will move closer to the surface, whereas during the day, the molecule will move away from the surface, go to higher altitude position. Why? That is because during the day, the surface getting hot very easily, as you can see in this diagram, after sunrise. So the surface temperature getting hot very quickly. As a result, the air molecule near the surface could gain the energy directly from the surface, either by conduction or convection. Of course, you can argue that radiation also play a certain role. But in this simplified model, we can simply accept that the energy can be transferred from surface to the air. As a result, the kinetic energy will increase. Because the kinetic energy is proportional to the square of velocity. So therefore, if we just follow the individual molecule near the surface of Earth, they will, as their kinetic energy increase, they can move faster. So therefore, they will try, because closer to the surface, the air density is the highest. So therefore, the easier way to get rid of this situation is actually move upward. So this is just one of the air molecule behave during the day. So eventually, the position change go to a higher altitude. During this process, the kinetic energy originally the molecule has at a lower altitude will be converted to its gravitational potential energy. You see that? And while the kinetic energy decrease. So that is why the temperature as a whole still getting cold toward the higher altitude. But the potential energy, the gravitational potential energy of each air molecule increase. So this is a natural way to store the thermal energy by the atmosphere in the presence of the gravitational interaction. So that is a very important feature of our atmosphere where we live. On the other hand, at night after sunset, the surface temperature drop very quickly. So the surface temperature drop very quickly. As a result, the the air near the surface getting cold, and the kinetic energy will be reduced or decrease. However, for the air molecule originally at a higher altitude with high gravitational potential energy will spontaneously drop. It's just like a free fall. If there's no collision, they just behave like a free fall. They will just move toward the surface. So during this process, they stored thermal energy in the form of gravitational potential energy will be transformed into the kinetic energy. In this case, the translational kinetic energy. So therefore, on the way back to the surface, the kinetic energy will increase. Hence, the air temperature will increase. So that is why at night, the air temperature above the surface is still higher than the surface temperature. It can act in two ways. One is to slow down the decrease of the surface temperature. Another is just make people feel comfortable at night, not as cold as the surface temperature. So it is simply the energy transformation process. To be specific in these two diagrams, I used m sub a to represent the total mass of atmosphere. Of course, you can, the mass would be the sum of all molecules. But as a thought experiment, we can introduce this block to represent the total mass of atmosphere. In this way, we can easily to work out the variation of the total gravitational potential energy. The position of this block is actually the mass center of atmosphere. So this is something you have to imagine. So therefore, use this nearly point mass model, we can work out the total potential, the total gravitational potential energy of the atmosphere at night. And we can also work out the total gravitational potential energy of atmosphere during the day. In this way, we should be able to work out the increment of the height of the mass center of atmosphere. In this way, we should be able to do some quantitative estimate. So on the left-hand side, let's first to work out the expression for the change in the gravitational potential energy. So this is a simple formula. Delta EP equal to MA, the mass of atmosphere, multiply G, the gravitational acceleration, multiply delta H, which is a change in the height of mass center. So this is a formula. So I got this number from this recent reference, say published in the Journal of Climate. But I wonder why nobody have actually used this idea to explain the diurnal variation so far. So this is number I cited, can you see? The total mean mass of atmosphere is 5.1 times 10 to the power 18 kilogram. So using this number, we can, 9.8 is gravitational, is a mean gravitational acceleration near the surface of Earth. So we can work out this simple expression for the variation in the gravitational potential energy of the atmosphere. To illustrate the capacity of this energy storage mechanism, I choose first the delta H just 1 meters. So in this case, the variation in the potential in gravitational potential energy is 5 times 10 to the power 19 joule. Okay. Another scenario, I choose delta H equal to 100 meters. not much, because our atmosphere is about 20 kilometer in its thickness. So this variation is not very big. In second scenario, the variation in the gravitational potential energy of the atmosphere is 5 times 10 to the power 21 joules. Okay, it's noticeably increased by 1,000 times. The reason I introduced the second scenario because I wanted to illustrate the capacity or how to appreciate the natural capacity of our atmosphere in its ability to store the thermal energy. In this diagram, in the block, I show you how to calculate how much energy the Earth absorbs from the sun during the day. So this energy come from the sun, can be represented by the solar constant, multiply this factor 1 minus alpha. Alpha is just albedo. If you go to any high school textbook, you should be able to work out this formula. Pi r square is just the cross-section area of this disk with the radius of the Earth, which is 6.4 thousand kilometers. So by putting these numbers together, these factors just represent the 12 hours during the day. So we can got this number very close to our second scenario. So what does that mean? It means that our atmosphere can easily store the whole solar energy absorbed by the Earth during the day in the form of gravitational potential energy by just shift its mean height by about 100 meters above the surface. So this is a very significant mechanism to understand the take for granted diurnal variation in the air temperature near the surface of the Earth. To appreciate this magic capability of our atmosphere, we really have to go to the thickness of atmosphere. Although in many textbooks and also the discussing of the greenhouse effect, layers of atmosphere are illustrated in these cartoon-like pictures. But what I can tell you, they are all totally wrong in their scale. The thickness of atmosphere compared with its radius is thin, not as big as this thickness. So forget about this diagram. So otherwise you will imagine that our atmosphere can acting as a magical mirror or emitters, as we discussed in my previous video. Here is more realistic illustration of the thickness of atmosphere. This scale is based on the fact that the diameters of the radius of Earth is 6.4, 6,400 kilometers. Excuse me. So using this scale, I can draw this 6,000 kilometer. This is exactly 6,400 kilometers. So this interval represents 400 kilometers. Okay. Now, if we use this more realistic scale to draw a scale of the 100 kilometers above the surface, that would be the case. See, So this is the ground. This is the ground, and this is 100 kilometers above the Earth. So our troposphere is actually less than 10 kilometers. Can you imagine? You can hardly see. Or perhaps I can use this, this diagram. So this origin spot represents that 100 kilometers height or altitude. So this diagram represents, this scale is almost 100 kilometers, 100 kilometers. So you can see that these so-called layers of atmosphere are all within this small origin spot. Okay, the troposphere or the stratosphere is actually this is about half of this scale. So now they just go to the real side. Can you see? If you enlarge this one, so that we can see the radius of the Earth, you will notice that the atmosphere is very thin. Okay, one can hardly attribute some magical radioactive properties to our atmosphere. Nevertheless, as we discussed today, the gravity discovered by Isaac Newton can provide the effective storage for the absorbed energy during the day and release that energy gradually in order to maintain that our biosphere, where especially human lived, is as comfortable as it is. So this is an important message to take away from this talk, that the diurnal variation of the air temperature near the surface of Earth is regulated by nothing but gravity. If you like this talk, please like and subscribe, and ask your friends to subscribe. That will give me more encouragement to make more interesting talks. Thank you for your watching, and see you next time. Goodbye.